Okay, so good afternoon. Today actually we'll be talking about the convolutional neural network. So this is just an improvement of neural network which we have seen yesterday. So neural network requires basically the application of appropriate identification of features, and then those features has to be appropriately being given to the network to get a result. So success of neural network will depend upon how well you have created the sample data sets, which is actually is well represented in a particular feature space. But in reality, actually, there may not be a possibility of creating such an environment or such a feature size. It may not be possible. So in that case, what we do is we start building a neural networks which can look into the data set itself and try to identify the different features. So from that perspective, the convolution neural network is one of the important image understanding or image classification, object classification, anything which is related to image-based analysis or any data sets which requires a kind of a spatial context to be understood. All such data sets can be computed using the convolutional neural network. So today actually we'll be seeing the basic component of the convolution neural network, and then what are the different ways to improve the earlier neural network or ANN based models That's what we will look into in today. So let's say that in ANN models, generally what happens is it is having a few disadvantages. So mostly in the cases is that generally the classification is whenever is being carried out, or regression analysis or any kind of feature distinction which you want to carry out on ANN network using the ANN networks, then what happens is the spatial orientations or the meaning of spatial context, especially the nearby pixel, it's an interrelationship. So that is also called a spatial autocorrelation data sets. It may not be possible in fully connected ANN networks, which we had tried yesterday to execute. In fact, if you look into the core data set which has been provided, if you change just the hidden layer, you'll see that there is a lot of discrepancies in your classification. The reason is the 100 samples which has been provided is not sufficient to give you a 6 classes which is expected in your output. But in your data set, you're having only 2 or 3 classes, which is quite dominant. Other 3 classes are very less. So you have to have an equal number of sampling points available, which is actually a true representative of in the spectral space. So in the ANN, generally what happens is it doesn't care about the spatial orientation. So whatever like shapes or the outer boundaries which you may see in an image, those things won't be interpreted unless and until you precisely define where exactly in the coordinate location the start of a feature. Like suppose you want to showcase one particular object. For example, let's say from the satellite imagery you want to build a systems to identify different houses. So for training purposes you have to exactly tell in an image in an image where exactly or at what particular pixel location, the x pixel location x and y, the object is actually starting, what is the width, what is the height, and this exactly has to match in your data set. If there's a deviation or discrepancies in that, then ANN will miserably fail. So that's why we call it the spatial orientation of image is not possible in an ANN. Then as you can see, the number of interconnection between different nodes like input, output layer, then hidden layer and the output layers. So if you increase the number of nodes in each layer, then the complexity of your parameter will increase. So it means like your number of samples will also be required to be very high. In fact, if you see, if you let's say in satellite image classification or the landside image classification itself, we were having in 7 bands, so 7 input band. On let's say in the middle layer we are putting it 8. So we are having an 7 into 8, that many number of connection between starting from input bands to the middle layer or hidden layer, and then again output there were 6 classes. So it means yesterday's if you see in yesterday's architecture or the classes which we had practicals, so there were total like this 7 input bands. In between we can have as many hidden layer nodes. So generally it is expected, generally it is being, thumb rule is being that if your number of feature classes is more, then the input hidden layer should be at least around the twice of that. So in our case, in the sample data set, if you look into that, so there are total 6 classes. So means this is the output layer which is having total 6 classes, and you are having a hidden layer. So over here we are having total 5 nodes. This is 6 node, and here we are having a 7 band input node. So if I see that how many weights we need, so since these nodes are actually connecting each of these node, so total number of connection parameter is approximately 7 into 5 into 6. So this is approximately 210 weight parameter which has to be determined. So it means like if you want to train properly this particular neural network, then you should have much more number of samples, or the number of sample at least 210. So your number of samples should be greater than 210, and the more you will have, then better it is. So that's in that case you will be able to use it. So you see that as the number of node increases, there is an increase in parameters. That parameter is nothing but weight, and the corresponding there is an impact. If there is a less number of parameter compared to the samples, then neural network may fail miserably. So in that case, if you use 7 bands, you may see in the output result may not be as meaningful. But if you reduce or decrease the number of bands from 7 to let's say 4, like blue, red, basically green, red, infrared or middle infrared, if you use those combination, then probably you will be getting a better classification result compared to the 7 bands which we have seen yesterday. So that's how we can say that in general the neural network, if you want to scale, or if you increase the number of input cells or input parameters, the corresponding there will be an increase in computational power, increase in number of samples, and so on. So later on, what has happened is people started slightly modifying this in networks, but in a completely different context. So that was basically inspired on the basis of that. This is also called self-learning, or the way the human brain works. So in that case, that is called the virtual cortex example. So in this case, basically a Gallant and has shown that generally whenever in any kind of mammals, whenever any light which goes or which basically falls onto the eyes, then that light only is not getting interpreted. There are higher level of representation of the information. So whatever information you have, which we extracted from our eyes, those information gets arranged into multi-layer organizations. For example, in this case, it is showing that at one layer, or that is at the retina level, you can see the disparity. So it means depth perception. You can see, you will be able to analyze the orientations and as well as directions from the any images which is formed in your retina wall. Then what happens is, again, all the information only gets forms on a specific cone. So like if you try to look at any features from your eyes, so your eyes at the beginning doesn't see them all of them combined together, but a small piece. So that's why we have a rods and cones. So each rod and cones basically looks or gathers only a very small amount of informations from the whole exposed area. Now all of those informations or which gets stored in your retina or cones, then all of them gets organized through the nerve tube, and then there is a spatial interrelationship and so on. So in that case, what basically in this picture we are trying to understand is that any kind of visual interpretations of a scene, whenever somebody wants to carry out, especially in the mammals, then that doesn't happen only on the intensity level, but rather than the connection of intensity and object identification happens with respect to the boundary identification in small sections and so on. So there is always a hierarchy of informations which get stored, and then finally in your basically in your brain, the final mental image is being formed. So that's how this is showing the complete flow of information at different levels. And then finally, when the high level object description is made available, so for the whole processing it takes around 100 milliseconds, which goes again for the further processing like decision making and so on. So this was basically the inspiration or the understanding of different human or any kind of mammal visual systems. So later on people started basically replicating that or mimicking that in a computational environment, which is called a representation learning method. So in that case, the information was being organized in a structured format, and that structure format it was expected that each of those structure formations, the different features which is expected or which can help persons to identify different objects can automatically be extracted and can be stored. So that became a part of de facto representation learning. So deep learning methods actually is a kind of extension of that representation learning. So it's basically tries to look for all the features which is present in your image data sets, and based on that it tries to organize the information in the hierarchical structure. So that's why you'll always see whenever any materials or on a web, you'll try to find out what exactly is the deep learning methods. So basically you will see that there is a kind of pyramid kind of structure. So that pyramid kind of structure has been inspired from the visual systems which we have discussed earlier. So in that case, in each of the structure level or the hierarchical pyramid levels, the information, whatever information is there, that information is expected to be representing a particular feature. So that's why we also call generally deep learning is supposed to have different it's basically a representative methods, and it always will have a kind of stack of level of representation. So it means that there will always be stacking of informations, in such a way that on each level there will be a kind of some features which will get created. Now, beauty of this CNN models is that it creates feature level informations where discriminatory classes or the cases in which you want to discriminate or classify two different or multiple different objects, the boundaries between two objects and distinctions should not be linear. So it means it will allow or supports the nonlinear representation also. So that's why it looks into the interdependencies between the different layers in a form of complex transformations that will let us to get or extract the hierarchical informations. So generally, if you take in terms of image case, so generally image will have only a set of pixels. From the pixels, different images will, different edges will be created, or different edges will compute or get interconnected will be a kind of motifs. So motif is nothing but a small portion of edge connected, and that edge connection, then when we combine them together, then it forms a part. So like for example, let's say from the satellite imagery, if your job is to identify basically one particular road network or maybe housing, so in that case the edges will be identified, so all the edges will be separate. Then inter edges, for example, generally houses are supposed to be of a polygon in nature. Most of the houses will be having a wall at 90 degree, so it means there will be a there will be angle between two lines which will be nearby at 90 degree. So those are actually those portion of the images is actually called a motif. So different edges and section of that which shows the interconnection between different edges, and that can be used for identifying the angles and all. So you can think of that as a motif, and combining all the corners is going to form a complete section of or complete outer boundary of an houses. Along with that, there are additional informations like texture and other information will also be combined together. Same is also is being case in case of speech recognitions. There are small number of phones. That phone is nothing but the sound of the words. Like in Hindi or in Sanskrit, we have the same number of phones, whatever we say. But in English, the letter is slightly different from the number of phones. That's why we have different representation in English. So all of these basically is being used, or basically the deep learning methods basically tries to build this hierarchical structure from going from lower level of informations to the higher level of information in CNN architectures. So deep learning is method which helps you in doing that. Out of those deep learning networks, there are an extension of that is called a CNN. So CNN basically, you can say a subset of DNN or DL computing architectures or DL computing methods, in which CNN is one of them. So CNN will consist of a list of networks, and each network layer will have some kind of filters on the top of that. So at next hierarchical structure layer, it will have some kind of specific informations that will get extracted. So generally it will be edges or some dominant features. For example, if you're having a car or any kind of vehicle, so you are supposed to have any kind of vehicle will at least will have a dominant feature called wheel. So there has to be a place somewhere where information related to wheels has to be stored. So it means like the feature, it will extract the feature in such a way that it will be able to identify the wheel component. Similarly, there will be some other features which might be present in the images. So combination of that is then going to give you a representation of the total objects, which help us in doing object identification, like from the satellite image or any kind of images, it tells what kind of object it is. Or then there are regional CNN models which also tells its locations. So like in object identification based CNN model, it will simply tell that one particular object is present or not in an object or in a particular image. That is the object identifications. But if you say regional object identification, then it will also give you the bounding box or approximate area where the system has found out that where exactly that object is lying. So it can do that, and that can be used for classifying the objects. And this also have a slightly lesser number of parameters because we don't have fully connected nodes from one layer to another layer. Rather than we can decide that how many maximum feature which we expect to be extracted. So generally that can be controlled on the basis of input data set. So if your input data sets are quite large, then you can look for a higher number of filters and corresponding parameters will be more, and it will also be a well trained. But if your data set are very less samples, so it means like if your images are, let's say 4 or 5, 10 different images, and you expect that using those 10 images, you want to build an CNN model which is going to identify that those objects which has been given in 5 or 4 images from anywhere in the place. So that will not be possible because the number of parameters which is required to extract from generally a CNN based parameters may not be sufficient enough. But as a whole, CNN will still require a very less number of input sample compared to the completely or fully connected ANN models. That's why it will have a kind of less data sets. So let's see that how does the deep classification network works. So when we say that there are a number of features, so at low level you just take a small portion of these images. So if my job is to identify an basically a car, then there should be some places in your image where it should extract some kind of edges, boundaries, and so on. So that's what we can see that in a lot of places it creates a filter which when it is being applied onto this image, then it is going to create a kind of edges and other formations. That can be interconnected at later stage to provide a higher level of features and classifications can be carried out. So as you can see, this is the image. So at one level, this is just a filter sufficient enough to identify different edges. So all these are edge filters, like it is changing, increasing and decreasing. So single boundary, double boundary and so on. So that's what we can see from the image. It's been given. It also looks for a kind of uniform texture informations. So there's a texture information which is present in this. So it is like in the images it is expected to have some kind of uniformity. And all these texture or uniform informations, there might be also some places in the images which may depict the heterogeneity which is present in your image. So let's say this whole image, there will be foreground and background. So foreground background extraction image can also be there. So all these filters actually represents one of these phenomena. So generally, anyone who is building in normal CNN models, they don't bother about all these filters. They simply hit and try different architecture, giving the kernel or different number of filters which can be applied. And then later on they just see and look into the data set and how well it is performing, and based on that the parameter setting can be changed. So that is basically an hyperparameter adjustment which is being carried out. That's what we do. But if somebody is really want to analyze layer by layer basis, or a person who is not simply user of an CNN models, but rather than a developer or somebody who is creating a unified CNN models, then in those cases we have to do an analysis of all these filters. We have to overlay these filters, or we need to apply all these filters onto this image, and finally you have to observe which particular feature it is going to dominate. It means like generally whenever we say output available from this feature, so what it means is that it will take this window or convolution window and you start applying this small portion of patch on this image slowly onto this whole image. So by stride of one, so it means take basically put this whole filter on the top of this corner, then you just fix one, you left by one row or one column, you just shift by one column, and again you compute the underlying multiplications and corresponding summations. So that's how you will get intensity values at the center of this whole geometry in these images, and finally you will get a result which has to be interpreted and understood, that which filter is working well or what are the other information which needs to be required or stored. Sometimes what people do is they also store the specific filter which during the analysis phase can be considered to be good enough. So the weight of those features are also get stored somewhere, and that can be used for can be marked for a specific purpose. Later on we can also use those filter without modifying it. So it means like that's basically an example of transfer learning, where the information or knowledge which is available in one network can be applied at another places as well. So these small features will then combine together is going to give you the outer or middle level features. So as you can see, this filter at the left hand side, or there are a lot of edge filters which are available here. So outcome of all these edge filters, if you see, that may have come across, and in the wheel we can identify. So generally any kind of images in which you want to identify the particular feature, like in this case car or bus or any vehicle objects or transportation objects, then in those cases in those cases the wheel is the quite prominent part of it. So it means like at the first layer there has to be identification of few edges, and then after consecutive or the next two layers you should see some kind of a prominent feature like this, which should give you an indication like, yeah, this the object has started, or the total learning process has identified this vehicle's car as one of this vehicle's basically tire as one of the component important features. So same way we can also say like there will be a few edge lines. So mostly dominant feature or edge lines will be always having horizontal orientations, so that can be there. So it means like there will be few combinations of all those features. So all these separate features, these will be available on middle level at middle level architectures, and finally what happens is all these middle layer architectures that gets compared in this case all the features, whatever features we are having over here, that can be used for discriminating different objects and classes at later stage. So on the basis of that we can identify different objects. So that's how the general deep classification level network information is being stored. And all these information, as you see, yesterday we made a vanilla kind of neural networks where everything starting from the weight, identification and all we did ourselves. So that weight information is being represented in form of feature like this. So if you see that generally in convolution, so this is basically a deep classifying or classification neural network. So in general classification or general CNN net architectures, what we are supposed to have is basically the some of the important layer which will be acting or working or providing a specific information. For example, This is just a piece of image and a small section of it. So these sections, basically what we do is we carry out a kind of convolution. So convolution is nothing but running the filter. So earlier when I said that small piece of image, this image has to be run through on the whole image, then finally there will be a dominant feature will emerge. So that's what we are seeing it over here. So all these filters is going to execute, and finally you will see a large number of separate features highlighting or providing a dominant component of particular objects, which gets highlighted or gets created in a filter. So once we create this filter, then there's always a kind of scaling. So scaling is basically work on a principle that if you have a very large image of any object, and if you reduce its size, the object's property or the way it looks will remain same. So there is hardly any impact. So if I just rescale this particular image again, so in this rescaled or smaller scale image, the picture of the raw object will remain same. So that's the gist. So in that case, there is a reduction in the scale dimensions. So that's basically that's basically happens in scaling part. So this scaling is being done with the help of max pooling. And max pooling is nothing but just a scaling of the features, and it works on a principle that even if you reduce or the scale, the corresponding objects or the features which has been identified at a particular layer is not going to change. That's the assumptions. Once we have that, and the other advantage of that is that if you reduce it, the size, then at later stage the connection required to the next layer will be a lesser one. So it means like there is a kind of reduction in parameters. So generally max pooling will follow with basically any convolution will follow through max pooling layer. So that max pooling layer is this or the rescaling layer, which ensures that the informations required to be transferred to the next layer actually gets reduced, and that in turn results in reduction in the number of connections and parameters and the samples and so on. So those are the advantages which goes on. So in any kind of CNN network, you'll be having a convolutional layer, then max pooling. So it means like after the scaling, the max pooling will be there. And after that, what happens is there will be a kind of normalization area, which basically what it does is that in each of the identified objects, what it tries to do is it basically looks for only the dominant features. So in an image, let's say if you try to find out the edges on an image, so there will be a lot of images. But the dominant images should be used which should have a particular length and so on. So same is the case in the convolutional neural network. Like at any layer, if one pixel is having some kind of, or any filter is having some kind of dominant features, then that dominant feature should that dominant feature only should be selected. Otherwise, there will be an overfitting of your data sets, and you may be having a very high accuracy of your data sets, but you may not get the result in on a testing after the training. Then if you want to do it, actual execution of that model or any actual data sets, that may not work. So that's why you need to have dominant features. So dominant feature existence is being done with the help of normalization layer, and then there's also a non-linearity component which is getting built in with the help of only transferring the information which is non-linear using different type of activation functions. Yesterday we have used sigma activation functions, There may be another activation functions that may also may be available in a neural network framework. So a lot of different activation functions are there. So the job of those activation function is to normalize the input, and as normalize the input, so it is only taking the important and dominant features, and as well as it also ensures that in informations, whatever information which gets passed on, there is some kind of non-linearity also gets introduced. That's exactly it helps in finding out the informations. So from the basic structures, you may have convolutional layer network. After convolution, you do a max pooling. So generally these two are getting twice. So once this reduction has been done, again you look for a new filter and apply this filter and do a again rescaling. So that's how the general practice in images identification is being carried out. But this reduction and other things can be considered on the basis of your scale. Let's say, for example, if your image tile size is 256 by 256 of let's say deep globe, which is having a 0.5 meter resolutions. So if I take an image of 25 by 25 pixel or 50 by 50 pixels, that means that in my whole tile or a filtered tile, which we expect that will have only 12.5 by 12.5 meter of informations. So any predominant feature which is existing in a scale of 12.5 by 12.5 meters will get stored in different layers. So that's how the at first layer, then again it will get reduced further. So it means like there will always be a reductions of your data set. So always there is a chance to choose an appropriate filter size. The window size has to be given, and that window size or kernel size should be taken on the basis of the feature which you are trying to identify from the input images. So if in the input images, the feature, whatever feature you expect is requiring, let's say, 36 by 36 pixels, then your window size should be of 36 by 36 pixels. So that's what we have to keep in mind. So mathematically, so this is basically a normal architectures. So mathematically, this can be represented in the form of first image segmentation, means creating some piece of those information, the small windows. Within that windows, you create a weighted sum of a network, and then finally you get an output activated functions, and these output activated functions then gets combined together to give you output. So now this in this layer, basically the after activations, the non-linearity start observing. So basically you are creating a functions which is taking activation as an input, and based on that the total feature is being identified, and generally the subsampling or stage is being carried out as I was telling on the basis of the image feature size which you expect to be present in your image. So let's say how the convolutional network works, or the convolution layer works. So it's basically taking an feature map which has to be generated. In this case, that feature map is going to be represented by a weight matrix. So this weight matrix is going to identify and provide the feature maps, and these feature maps or weight will get updated based on your data sets. And yesterday we have seen that there was a weight update method. So weight update method actually is nothing but after the backpropagation error method, the weight has to be updated, and that weight updation methods can be carried out when the whole batch of image has been processed, or maybe after each sample images. So this strategy will let us to identify a particular way of updating the weight. So that is called that's being used in the deep learning architecture. So once you identify this weight approximation updations, so that basically helps you in identifying and creating an appropriate feature map. So it ensures that the convolutional layer's basic objective is that anywhere in your image, the spatial context or the interrelationship between different pixels, whatever you have, that should be stored, or that should be captured by each of those filters. That's why it has to be taken, it has to be created where spatial context is being built in. And all of them are again going to weight onto different layers. So what it means is, let's say if you're using an image which is having a 5-band or 3-band, so dominant features which will be the outcome of a convolutional neural network, it will actually is going to apply on all the bands equally. So is the dominant feature is going to be extracted on different bands in an equal manner. So that's the important aspect which we need to understand. That's why it is called a shared weight. If you don't have a shared weight, then it has to be arranged and rearranged in a different way. So in that case, the feature identification at different layers can be carried out in a different way. Otherwise, by default, in any kind of convolutional framework is going to share the weight across all the convolutional band. So this how it is getting created. So in the convolutional neural network, all the input patterns or the spatial grid values gets interconnected in a multi-layer format, and these multi-layer format is going to construct a kind of receptive field. So such layer gets repeated. So let's say 5 or 6 different sample at nearby gets put it into a context information extractions, and that can combine together and can provide a spatial dependence. This is the way we get the convolutional nature of the interdimensional spatial information, which was missing in case of normal neural networks. So this basically shows that on each output layer, which is being shared by a different band, so all the values will get copied from the previous layer to the output layer's band, and that's why it is called a kind of feature, basically a shared weight mechanism how it's being carried out. So this also helps in reducing the parameters, because if the shared weight parameters, shared weight knowledge will not be used. So in this case, in this tiny example, the overall execution time will go by 3 times. The reason is that the weight again needs to be recomputed for another 2. So it means like there will always be a computational intensity which is going to increase in a convolutional neural layers. Then nonlinearity, there is a lot of different choices. So by default, in most of the cases, you will see or you hear that basically the neural network is using an activation function which is ReLU. So ReLU is nothing but a kind of response like this. So if the weighted sum of all the input values, if it is less than 0, then nothing is going to happen and the output will get generated by 0. Otherwise, what will happen is whatever value is coming, that value will get added. So this is basically, this particular thing is being written in form of functions where you have to use max of 0 or the computed weighted values. So there are other functions like tan hx or sigmoid and so on. So this all these functions helps in or these separate nonlinear active function can help us in identifying the or fitting the data sets which is normalized and and accordingly it can improve its efficiency. So always all of these data sets are expected to be a normalized one. If you don't normalize it, then there will be a kind of instability in such data set. But in any way, the activation function ensures that output is not whatever the weighted sum is coming, but rather than there is a deviations based on the conditions. So either it may be a conditional one imposed directly, or there will be a condition which may arise due to some other evaluation metrics. Then in the next stage there's a pooling layer. So pooling layer, what it says is basically reduction in scale. So as you can see in this image, that whatever feature was there, if you downsample it, the feature arrangement remains almost same. So if that is the case, then in such cases the scale reduction is not going to affect the actual feature which is present in this. So max pooling basically ensures that out of those smaller windows, whatever the maximum values is there, that is getting transferred. So that's how the max pooling approach actually works. Apart from that, in CNN you may have some other networks. Generally, if your task is to do classifications, then in that case you may be having a lot of convolutional activation value network, and then followed by max pooling or pooling. Then there's also an average pooling. So there may be a lot of average pooling. So these three components may go on and on, so increasing the depth of your whole network. But if your job is to have a classification, so just before the final output, you need to flatten all the input layers. Like in this case, for example, let's say in an image where you're having a 3x3 windows. So just before the end of first layer, what we can do is we can create complete linearization of the whole matrix. So instead of having 3x3 matrix, we can have 1x9 matrix. So it means like that's the way it will get flattened. And once it gets flattened, then we can create or connect the ANN models for doing an appropriate classification. So you see that ANN is going to give you an appropriate output only when your input feature are well enough defined. And the whole purpose of the CNN modeling technique is to just your network learn about the important features and create those features, which features can later on be used for fixing the basically the different data sets. So different data sets into different categories. So that's how the fully connected network works. So this is just an example. If you want, you can have a look of these examples. The complete working example is available on GitHub, and you can try it out. So you only need to download the additional data sets, and using this you can execute and run the whole model. So this requires a kind of basic understanding of TensorFlow framework. So tomorrow we'll just look into one of the basic building blocks of such models, Keras, TensorFlow and PyTorch, how such frameworks can help us or make our life easier to construct a CNN based model with a very less amount of effort for doing a task like this. So you're having a vector data, you will create a mask or representation of those data, then you have to create it multiple batch of the smaller piece of the images. So let's say in the satellite imagery you may be having 6000 by 6000 or 5000 by 5000 pixel, but during the CNN classification you don't use the whole tile image rather than a small piece of that. So for that you have to break it down into smaller piece, and you need to ensure that each of these smaller piece of images is actually containing the information which you want to identify or classify. If this smaller patch is filled with only one particular dominant class, then in that case at max result after the training you can expect is that the whole tile will be tagged it either one class or the another class. Like in the first lectures we have seen that there are four categories of satellite imagery, like water, or the cloud, or the desert areas and so on. So if one full chip is having all the single features, then in that case the whole chip will only get identified at one of the classes. But in the cases where you want to identify the objects itself, let's say my job is in the satellite imagery, I want to identify the different roads or houses, then in those cases you need to ensure that a smaller piece of patch, that is 256 by 256 image, which has been generated from the very large set of satellite imagery, it should contain those features in specific regions, and those regions size should be good enough for good representative of different filters, and at least at layers nearer to your input cell. So once you have all these, then what we can do, we can create a result which we can create a model, which at later stage what it can do is it can do a classification of the different satellite images. So if you see, there is a kind of one-to-one correspondence between different prediction and classification scheme. So this is just an example where linear feature properties like connectivity, contiguity. So generally linear feature are expected to have a connectivity across the region. There has to have a contiguity, so it means there should not be any break. Then there will be a particular place where junctions can be created and so on. So all these junction, connectivity, contiguity properties which we generally create with other methods gets automatically identified in a CNN based models, and then it's provides the corresponding output. So with this we are ending